So what I'm going to do in the next 20 minutes is basically, I hope to take away the magic of it and show you how it really works. So I'm going to skip the mathematics, I'm going to skip the gory details, and what I'm going to give you is sort of a historical overview of inverse scattering, especially as to how it pertains into the way we do Marchenko imaging right now. And so the cool thing about Marchenko imaging is, and I'm going to give you sort of an upshot first, is that we can focus wave fields in an unknown medium because the quantity that we solve for is the Green's function. And that is all we need to get from our acquisition surface to our focusing point inside the medium. That's it. Thank you for your attention. So I need to explain that. So, let me first take you back 50 years. This was the time when Marchenko formulated his inverse scattering algorithm. There is a certain potential V of x. This was for one-dimensional Schrödinger equation. That was the context at which he worked. You send in an incoming wave from the left. You record a reflected wave with a certain reflection coefficient as a function of wave number or frequency if you want. And the job is to estimate the potential from your reflectivity, from your reflection data. And this problem, believe it or not, has an exact solution. There's no approximations involved. And not only that, it is stunningly simple. So what you do is the following. You take your reflection coefficient and you go from the frequency domain to the time domain. You stick it into that integral equation, and it looks nasty, but that integral equation you solve just for one value of x. You want to construct the potential at one location of x, and you are completely free to pick any location that you like. And you solve that unknown function k as a function of time. So x is just a parameter that is fixed. Once you do that, you take this derivative and voila, there's your medium. That's it. And this is completely exact. There is no approximation. And there's something really magical about this. And that's the following. You measure your data at a measurement point. In this case, it's x is equal to 0. And what the algorithm allows you to do is to reconstruct the medium at any location x in the interior of your medium. And you don't need to know the medium between your observation point and your reconstruction point. That is the magical thing about this. And I'll explain to you how this works. So the main question I want to address here, and that is still a relevant question for us as geophysicists today, 60 years later, is why don't we need a model between the acquisition and reconstruction points? And specifically, why don't we need a model to focus wave fields in an unknown medium? That's the same question. And the short answer is, well, it's Green's theorem. I mean, you knew this all along. I mean, Green's theorem basically tells you that if you know your wave field at the bounding surface, and if you know your Green's function, you can compute the wave field at any point in the interior of that surface. I mean, this is, what is it, Calc 2 or something. And so, basically, if you know the Green's function, you have a recipe to take your wave field from your acquisition surface to any point in the interior. So if you know the Green's function, this is all you need to know. If you know the Green's function, you don't need a model. If you know the Green's function, you don't have to do modeling. No more finite difference calculations. If you know the Green's function, you can target-oriented imaging, because you can compute this integral only at the area that you're interested in. And you can compute the wave field everywhere in the interior. You can stick it back into your wave equation and you immediately get your medium parameters. So, getting the Green's function is really key. So I first want to show you some data examples on where we have been able to get the Green's function directly. This was a study we did about 7 years ago, seismic interferometry with USArray. What we did is we cross-correlated the wave field at a station indicated with a star. Just the seismic noise indicated at the wave field at the station indicated with a star. With the seismic noise recorded at all the stations indicated with triangles. It's a time lag cross-correlation. We show it for 2 lap times over here, and you can see that the station shown by the star acts like a virtual source that radiates a quasi-circular wave field propagating through the western part of the United States. This is the surface wave. Now we know the wave field everywhere in our medium, at least at the surface, which for surface waves is all you need to know. And then we developed iconal tomography to translate these wave fields into the medium properties. But this is sort of cheating because now we had stations everywhere. So I want to show you another example, which is by Jim Greenleaf and co-workers. And they work in medical imaging. And they developed a technique, it's really cool, it's based on magnetic resonance imaging, MRI, which allows them to take snapshots of the shear waves that propagate through soft tissues. So with MRI they can literally take snapshots of the shear waves that propagate through a body. It's really cool. And here you see the shear wave that propagates through an agar sample with a little inclusion in it. You can immediately see where the inclusion is, of course. I mean, here they have the whole wave field. By sticking it back into the wave equation, they can solve for the shear stiffness, and you can immediately see where the inhomogeneity is. This is a really interesting technique, which unfortunately will be difficult for us to do as geophysicists, but it's really cool. Here you see, on the right, you see the brain of a volunteer. This is a student, by the way. They always use students as volunteers. So, students among you, count your blessings. Okay? And the image is also interesting, but I want to point you to part of the caption, which says that shear waves were generated in the brain at 100 Hz by applying lateral motion to a thermoplastic bite bar held in the teeth of the volunteer, the student. And the main point I want to make this is that if you can measure or if you can reconstruct the wave field directly, it doesn't really matter what source you use. The source might just be some vibrator held between the teeth of a volunteer. It doesn't really matter anymore. Because once you know the wave field, you know the medium. And this is a picture, it's so cool, I just had to show it to you. Here are shear waves propagating through the biceps. And the biceps is not lifting anything on the left, and on the right is lifting 8 kilograms. And you all know that when you lift something, your muscles harden, the shear modulus increases, and so the wavelength of the shear wave increases. So, knowing the wave field in the interior of a medium is everything. So now I want to come back to that whole question, why don't we need a model between the acquisition and the reconstruction points? And I'm going to show you some figures in a paper by Bob Burridge in 1980. And he used all these figures as graphical derivations of his infrascattering equations. He didn't give the physical interpretation, which is too bad, because he could have saved us 35 years of work. He analyzed the plasma wave equation, which is an equation at which waves move at a constant velocity. In this case, the velocity was equal to 1. And what you see here in the dotted area is the area where the Green's function lives, which means that if I place a source at x is equal to 0, I radiate waves, and these waves are causal. All the waves arrive after the direct wave, and that is why all the energy is located in that triangular cone. You know, if you're into relativity, you would say that's the light cone. Everything has to live in the light cone. Okay? So this just tells us that the Green's function is causal. Now, that function k that I showed you earlier for the Marchenko equation has a support as shown in the right figure, in the striped area. So it also lives in a cone, but the cone is rotated over 90 degrees. That means it's not a causal function, it's an acausal function. What is it? It's a solution to the wave equation where we only get a response to the right of the point of excitation. So this is a special solution where the waves only move to one side of the excitation. And this solution turns out to be very essential in infrascattering. So you can show that if you want to have a wave field that is only non-zero to the right of the source, you can only create that if it is acausal. You must have incident waves that conspire together with the source to give you this wave field. But this function k that is shown over here, or the support of the function shown over here, is exactly the function that you reconstruct with the Marchenko equation. And I like to call it's a right-going Green's function. And this cartoon actually explains sort of the riddle of why we don't need to know the median between our observation point and our reconstruction point, because the function that we are solving for is the function that takes the wave field from our observation points down to our reconstruction points. So that's why I call it a right-going Green's function, and we recently started calling it a focusing solution. This is what you see in the papers that we have written. We call it a focusing solution because you can see that the wave field sort of focuses at the tip of that triangular area. Now, the focusing solution and the Green's function, they're shown over here. They're separated by the line x equals t, which is the arrival time of the direct wave. And what I'm going to show you later, and what you're going to see in all our work on inverse scattering, is that we need to know the arrival time of the direct wave. You can find it in each and every one of our papers. And we need that because the arrival time of the direct wave separates the Green's function from the focusing solution. And this is why, although we like to say that we don't need to have a detailed model to focus inside the Earth, it's not quite true. We must have what we call a macro model that allows us to predict the arrival time of the direct wave. So this is why all the inverse scattering work that we've been doing relies on a macro model of the velocity and the reflected waves recorded at the surface. Exactly the same ingredient that you need for any type of imaging. Now the Green's function, the data and the focusing solution are connected. Here I show the Green's function again. This is where the data live. They live on the red line. They are the wave field recorded at the location x is equal to 0. So that's your reflectivity as a function of time. On the right panel you now see the Green's function and the focusing solution. And there is representation theorems, and graphically I indicated it by the blue lines that relate the focusing solution to the recorded data, which are your reflected waves at the surface. So that's how it all comes together, and that's why we can reconstruct the focusing solution based on the reflection data, because the representation theorems tie them all together. Now, the physicists didn't really care about this. The physicists, they cared about medium reconstruction. They wanted to know a potential based on scattering data. And this changed in the early 2000s when James Rose came along. He started using the word autofocusing, and as you can see in his abstract, he says, given single-sided axis, how does one focus sound to a point at a specified time, given that the velocity profile is unknown? And he basically showed that that's actually what those Marchenko equations are doing. This is an example of his paper. You see a velocity profile indicated by the red line. There's two incident pulses coming in from the left, and they conspire together to give you a focused wave field to the right of the inhomogeneity. We did the same thing. This was what Filippo Borghini did. He showed it like 3 or 4 years ago at the CWP meeting. We looked at an acoustic medium where both the density and the velocity had variations that were independent of each other. You see the models over here. So we had 2 medium parameters and 1 reflectivity. And the question we asked ourselves, can we still focus in this case? Because you might think you might not have enough data, because you have 2 unknown medium parameters, and 1 piece of data, the reflectivity, can we still focus here? And I will show you that we can. So first of all, this is the Green's function. This is a numerical simulation, so we just put a source inside that medium. Again, you see the equivalent of a light cone. The only thing is the sides of the cone aren't straight anymore, because now we have a variable velocity. But still we get a causal response. This was the solution of the Marchenko equation that Filippo obtained. It looks sort of messy. It doesn't look like anything focuses. But if you make a cross-section of this solution at time t is equal to 0, you get the wave field that is shown in the lower panel, and you see a nice peak at time x is equal to 0. Okay. This was the type of focusing that Jim Rose talked about. But this is not what we wanted, because the wave field that you see here doesn't really collapse onto a point. So Filippo and I got stuck for 5 months. We just scratched our heads. What we didn't know was that if you look at the wave field to the left of the red line and to the right of the right line, they actually contained the solution to the riddle, because the wave field to the right of the red line is the Green's function, and the wave field to the left of the red line is the focusing solution. But we didn't see it at that time. So we asked ourselves then a question. Oh, by the way, and I want to show you that the figure that you see on the right is the same as the figure that I showed you earlier of Bob Burridge that I now flipped around in space. But on the left side you have the focusing solution, on the right side you have the Green's function. It was all known since 1980s, we just didn't know it. Then we ask ourselves the question, well, how do we get the Green's function from this solution of the Marchenko equation? And we noticed that the solution for the wave field to the left of this red line is antisymmetric in time. Wherever I have a positive polarity in the upper part, I have a negative polarity in the lower part. And that, of course, was the recipe how to get the Green's function, because this is what you do. You take the solution, you flip it around in time, you average, and there you have the Green's function. There you have a wave field which is completely focused on a point in the interior. In fact, let me compare the causal part of this Green's function, the blue box, with the Green's function that we computed directly. Up to a scaling factor, it is identical. Of course, what you get is acausal. We also find a solution for negative times, and that is because we have created a virtual source in the medium. There is no real source, so the only way in which waves can radiate away from a virtual source point at positive times is that waves are incident on that virtual source point at negative times. So here you see it happening. So now let's go to 3 dimensions, and I'm going to show you how the focusing solutions works, how they are related to the Green's function, and how that is related to imaging. So we acquire data at a surface, and as Satyan will show you next, this can either be a free surface or just a transparent surface. It doesn't really matter. There is an overburden, and then we want to focus wave field at some focusing level, and specifically we want to focus wave field at a target point which is indicated by the red dot. So the Marchenko equation gives us a recipe to find the focusing solution. It's the wave field that is incident on my focusing point, and as Satyan will show you, all the internal multiples, all the surface related multiples are correctly handled by the Marchenko equation. Now the wave field focuses to a spike at our focusing points, and now if we let that wave propagate into the subsurface, it becomes the downward component of the Green's function. And that's the beauty of the Marchenko imaging that we developed, is that we don't just get the Green's function, we get both the downward component of the Green's function and the upward component of the Green's function at our target point. And I'll show you how you can use that directly for imaging. So the Marchenko equation gives us now, at any desired point in the subsurface, the downward and the upward component of the Green's function that take care of the downward continuation. No more modeling, no more model estimation. We don't need to know where the reflectors are. All the multiples are taken care of. It's completely target oriented. We can do it at one point in the subsurface. We can do it at a horizontal surface. We can do it in the box. We can do it anywhere. And we can use, and that's what I'm going to show you next, we can use these upward and downward components of the Green's function directly for imaging. And there's 3 ways of doing that. Actually, there's 4 ways of doing it. I've told you already one way. You take your wave field, you stick it back into the wave equation, you solve for your medium parameters, and you're done. So that's already the 4th way. So let me now explain you the other ways. So at your target point, you know the upward and the downward component of your Green's function. And if you have a reflector just under your target point, then you know that the upgoing component is equal to the reflection coefficient times the downward component with a certain phase factor, because your target point is quite at the reflector. Now, if my target point is at the reflector, then tau goes to 0, and in that case your reflectivity, your imaging criterion if you want, is just the ratio of the downward and the upward component of the Green's function. To be more precise, your image is the deconvolution of the upward and the downward component of the Green's function evaluated at time t equals 0. That's one scenario. The other 2 scenarios are more complicated. So let's say you have an acquisition surface, you have a horrible overburden, think of salt, there's a target below, you define a reference surface, and you apply your Marchenko imaging condition to any point on that reference surface. So now you know the upward component and the downward component of the Green's function at any point at your reference surface. Now these upward and downward components are related through a reflectivity operator, because any wave that goes down from my reference surface is being reflected upward from the reflectors under my reference surface, and it becomes an upward going wave. So there's a reflectivity operator that tells you how a downward going wave at a certain location on your reference surface is turned into an upward going wave at your reference surface. And the beauty is that you can take that integral equation that you have, the integral that you have at the bottom, and just solve it for your reflectivity operator. And this is what is called multidimensional deconvolution, which has been spearheaded by the Delft group, with whom we closely collaborate. So what does that operator do? It basically gives you the response to a downgoing virtual source at the location x prime that is recorded on all other locations x on your reference surface. That is now what you have obtained. And the beauty is you get that reflectivity response for a medium that is homogeneous above your reference surface. This is what John Claerbout started talking about when he introduced Noah's deconvolution. We really are doing Noah's deconvolution, but we're doing it in more than one dimension. John Claerbout introduced the concept, I think it was in the 1960s, for a one-dimensional medium, but you can generalize that for multidimensional media too. So now you have that reflectivity, and now there is two ways to do imaging. The first is to say, well, let's set a point x is equal to x prime and evaluate the result at t equals 0. That's basically, I get the reflectivity at my excitation point at time t equals 0. That should be the image. So that is one way to do it. The other way to do it is to say, well, you know, I have my reflectivity now everywhere on this reference surface. I have stripped away the imprint of a complicated overburden. Now I can do standard imaging below. I can do spherical migration, reverse time migration. It doesn't really matter anymore, because now you've taken away the complicated overburden. So that's the other way in which you could use this for imaging. So I hope I've clarified some of the concepts that lie behind the whole work on Marchenko imaging, on infrared scattering, and the way we are working towards applying that in seismic applications.